1.8. So we're going to be looking now at section 1.8. And so grab yourself a tea. That's what I got. I got some tea going, and it's going to be great. You're going to love it. So let's get going on it. So continuity and limits is what 1.8 is talking about. And I give you the informal definition of continuity. A function that when graphed has no breaks in it, that is, no vertical asymptotes, no jumps, and no holes, is continuous. And so, and this is problem 4. They ask me, from the graph of G, state the numbers at which G is discontinuous. So that's what they're asking us to do. I want to add on here something else happening that they didn't quite have. So here, I'm just kind of adding it on here. There. And I don't know why I put -4. Okay, so from the graph, they want us to state the numbers at which G is discontinuous, and so those are going to be values for X, where it's discontinuous. So we're going to either have a hole in the graph, or a jump in the graph, or a asymptote. So right here at -2, there's some issue. There's no issues here, but at -2, there's a hole. So X equals -2. There's a hole in the graph, right? And then at -1, there is an asymptote. So they usually ask you for the X values of problems on the graph. So there's a problem, an X at the coordinate X equals -2, and at the coordinate X equals -1, there's a problem. And also at 0, we have a problem. And so we have a jump at X equals 0. So the numbers that we're going to have problems at are -2, -1, and 0, and also at 1. And so and also now I've added on here at 3, a little hole in the graph. Oh, excuse me, at 4. Okay. And then they tell us about the continuity checklist, and they're wanting to define continuity based on limits. And so the checklist starts off here. If f of a is defined at a place A in the domain, so in order for f to be continuous at A, the following 3 conditions must hold. That f of a is defined, that the limit of f of x as x approaches A exists. By the way, if something's going to plus or minus infinity, this condition is not held. And also a third, that that limit is equal to f of a. So these two from 1 and 2 are equal to one another. So they want us to look at, for all the things found in part A, state the conditions. So these are our values for A that we're looking at places. They want us to say which part of the checklist is violated, and it might be more than one part of the checklist. So the first one is at -2. And so f at -2, when I ask myself about it, right, is, well, f of -2 wasn't defined. And so that's the reason it's not continuous there, is because this was undefined. So it violated 1, right? And so of the checklist is what it violates. So violated 1. Now it might violate other things as well, but it violated the first condition. And then the next one at that asymptote, well, f at, what was it, -1, is also undefined. So it violated also 1 of the continuity checklist, that f of a is defined. Now the next one, at 0, f at 0, Well, f at 0 is defined. So this is the first thing I think about, and that this is defined. It's this value right here. So the next thing I think about, well, what about the limit as x goes to 0 of f of x, right, from our function? Ah, it's g. Are you kidding me? Sorry. It was g. So g at 0 is defined. Now I'm finding the limit there. I can see that the left limit is some value up here, some positive value, where the right limit, if I'm looking at it from the graph, is some negative value. And so this is what is being violated. This is does not exist. So this violated condition 2 is what it violated. And then at 1, some of these are almost the same, huh? So when I think about g of 1, it's defined, so no problem there. And when I think about condition 2, the limit as x goes to 1 of g of x is, as I go here closer and closer, right? Go here closer and closer, the limit doesn't exist. Do you guys agree? So it does not exist. And so this violated number 2. And the last one I want to verify is the one that I kind of drew on there because they didn't have an example that was just like that, but I wanted to make sure. So when I look to do it, I'm kind of out of room over there. I can fit it in, and that way they'll all be lined up. So when I do here, g at 4, it's defined. So check, right? When I do the limit as x goes to 4 of g of x, it's equal to some value from the left side and from the right side as you get closer and closer. Whatever this height of this hole is right here, right there, whatever that height is, that will be the limit. And so it exists. Because I don't have coordinates, can't tell you what the number is, but I can tell you it exists. And the third is that the limit as x goes to 4 of g of x would have to equal g at 4. And that's what's not true. And so this value right here is whatever height that would be this, and that's not equal to that value there. So those outputs, and so this is the one where it fails. And so this one violates number 3. So that's what they were asking us to do, is they were asking us to look at the continuity checklist and see which one does it violate. If it violates 1, there's no reason to go on and see if it violates 2, but it might. And so I usually, so anyway, so that's kind of the story there. So going on with this problem, they say they want me to state the intervals on which A is, on which the function is continuous. And so that's what they're wanting me to do. And you kind of have to use this idea of continuity when you come to some endpoint from the left or from the right in order to do that. And so here, as I come from the left, I have a hole in the graph. And so it wasn't continuous there because of that hole from the left or from the right. And so whereas this one right here, when I look at the limit as x goes to 0 of g of x, that does equal g at 0, right? And so if I stay on the left, so this one has left-hand side continuity, right? Do you guys agree? And so it's continuous at that point. So when I go to write this in interval notation, I'm kind of trying to look. It looks like we start here at -3. And then we have the problem, a hole, but that's not left-hand continuous or right-hand continuous at -2. So I'm going to leave -2 out. And then I have more continuity from -2 to -1. So in between there, it's continuous. But at -1, we have the asymptote. And then from -1, but this is where it's a little bit different, to 0. And I would put the bracket because it actually has left-hand, it's actually left-hand continuous there. And then going here from 0 to 1, so it's neither left-hand continuous or right-hand continuous here, because if you look at the left, the limit as x goes to 1 from a little bit smaller of g of x is not equal to g at 1, right? This is not true. And so, and it doesn't have right-hand continuity there either. And so this is going to be from 0 to 1, and then 1 to all the way to 4. And then I guess the way I've drawn it, from 4 to infinity, right? So the way I've drawn it, it looks like it's going from 4 to infinity there, because I've added on some stuff and it's all continuous at the end. So they're just telling you to watch the left hand and the right hand continuity, and the only place that we had left hand continuity or right hand continuity, either one, was at x equals 0. So anyway, so that's the story. What do I say there? Did I want us to fill in something, or was I just trying to make a note that 0 was different because it had the left-hand continuity? Textbook definition 3, if g is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuity from the right or from the left. And so we have actually that here also at -3. That had actually was actually right-hand continuous there at -3. And so, and I just noted, make sure that you look at the left-hand continuity there on 0. So I was just reminding myself to mention that, I guess. And then it says determine whether the following functions are continuous at A. Use the continuity checklist to justify your answer. And so on the checklist, the first thing would be to find f at A and check it out, right? So if I try to find f at A, in this case f at 5, right, that's what I want to find, that would be equal to 2 times this squared plus 3 times this plus 1 over this squared plus 5 times this. So I'm going to be plugging in, and it was -5, and I don't know why I missed the negative when I wrote it there, but I did. So I'm looking at this, and I'm noticing that my numerator, and it actually doesn't matter if my numerator is 0 or non-zero, but what would not be okay to be, what would make it undefined, is if my denominator was 0. So my numerator actually is, and like I say, when they're asking me to find f at -5, I don't care what the numerator is. That's different than finding a limit, right? Different than being asked to find a limit. This is saying exactly at -5. And 3 times -5 plus 1, hopefully that's the numerator, and I got 36. Over, and in the denominator I'm getting 0. And so f at -5 is undefined. And so it violates the continuity checklist number 1, and so it's not continuous. So that's what they were asking me. So it's not continuous at Now, here's where your book is wanting to say a specific point. So that's why they say at a equals -5. And a lot of students will say x equals -5. And I'm okay with that too, because I think they're wanting to make sure that you don't get confused and think it's a line, and I think that they're also wanting to make sure that you know that it's a certain point in there. And so I'm good with either of those, I guess. And then I'm just asking you this: do you think it's a whole or an asymptote? And so what would make us think it's a whole is if it was 0 over 0, then I would have to investigate it as being a whole. But if it's not 0 over 0, then I know it's an asymptote. So this is asking us, is it continuous at A? Use the continuity checklist to verify your answer. So the first thing I want to find out is, what about f at A, f at -2? Is that defined? And the answer is, yeah, it's equal to 1, right? If it's x is -2, so great. And then what about the limit as x approaches -2 of f of x in this case? So that's what I want to find now. Now, all I want to know is it defined, does it exist, or is it does not exist? And so you have to, because it's piecewise defined here, you want to look at the left limit and you want to versus the right limit, because something's happening at -2 and that's where we're going. So when I look at the left limit, this is as x approaches 2 from a little bit smaller than, and you would use this function. So you would use this function here as long as you weren't exactly equal to 2. So as I get closer and closer to 2, this is 1 over 0 is what that is. And so that is, and I could care if it's positive infinity or negative infinity, and I could figure out what it is, because it's over 0, I know that it is an asymptote, and I know that it's either going to positive infinity or negative infinity as I approach 2. And actually, I don't really care, but because this is a little, wait, this should have been -2 from a little bit smaller than, so now it is really 0. I don't know why I wrote 2, and then I was looking at it and thinking, so I wrote the wrong thing and then was thinking the right thing, and then I now put it back in here. So this is, if I'm a little bit smaller than -2, here's -2 and here's -3. If I'm a little bit smaller, I'm over here. So that's numbers like -2.1 and that kind of thing. And so this is really negative in the denominator, nearly 0, but negative. So this is really going to negative infinity. I actually didn't care which one it was going for, because right the minute that this is negative infinity or positive infinity, I know this does not exist, right? Now, this could also be negative infinity, and I wouldn't care because it has to exist. And so I'm going to say that this is not continuous. At A equals -2, it violates number 2 in the continuity checklist. And so here is a theorem out of your book. It's Theorem 5 and Theorem 7. They say that you can use direct substitution to find a limit of a linear function, a polynomial function, or a rational function, provided the denominator is not 0. So in the checklist, 1, 2, and 3 would hold for all linear functions and all polynomial functions at all points A, where A is in the domain, right? And so remember the continuity checklist says, number 3 of the continuity checklist says that the limit as x goes to A of f of x is equal to f of A. And what they're pointing out is that if you have a polynomial, it'll f of a will be defined for all values of a. And if you have a polynomial, f of the limit as x approaches a of f of x, if it's a polynomial or a linear function or a rational function, the limit will exist as long as you're in the domain. And then these two things will be equal for every polynomial, and would be equal for every rational function as long as, and what do we have to be careful on a rational function, as long as our denominator, as long as that value for a doesn't make the denominator equal to 0. And so it would be at all points a except where the denominator is 0. And so that would be kind of the story there. So in other words, the following types of functions are continuous at every number in their domains. Polynomial functions, because their domains are all real numbers, and rational functions are continuous except for where the denominator is equal to 0. And then root functions, they just make a note. So this is Theorem 5 and 7, and I just kind of wrote out what the theorems say. You're free to go look in your book and watch them. The domain for an odd root function is all real numbers. So if I said to you, what is the domain? In fact, this was a question that we had on the homework of something like this. Well, it's an odd root function, the cube root, and it's all real numbers. And so I don't even have to be careful. But an even root function, if I'd had an even root function, I'll put the same radicand, it doesn't matter, the square root function, then you have to make sure that you stay where your radicand is positive. That would be part of the domain. And then it would be continuous at all points where in the domain. And then trig functions, they just make a note that the domain of sine and cosine is all real numbers. And the others are slightly more tricky, but if you write as sine and cosine, you can see what the domains are pretty easily. So if you write tangent as sine and cosine, you can see what the domains are, and you don't want your denominator to be 0. So then essentially you've made it into something that is a fraction, and so you have to watch out for 0 in the denominator. And then they tell you another theorem, so I say some more theorems. Theorem 4, and this is on continuity, if you have two functions that are both continuous at a, then if you add them together, you'll get another function that's continuous at a. If you subtract them, you'll get another function that's continuous at a. If you multiply by a scalar like c, you'll get another function that's continuous at a. And if you multiply them together, you'll get another function that's continuous at a. If you divide them, provided that the denominator around a is not 0, then you'll get another continuous function. You can also raise to a power, and you'll get another continuous function. And you can also compose them. And provided that f is continuous at g of a, you'll get another continuous function. So this is 42, and it's asking you for the function, find the numbers at which f is discontinuous, sorry. And so what I want to think about and look at is, this is a polynomial, so it's continuous on its domain, so there's no problems there. 3 minus x is a polynomial, and it's continuous on its domain. It's a linear function, and so no problems there. And the square root would only have a problem if you tried to make it take the square root of a negative. But it's saying that x is going to be larger than 4, and everything larger than 4 is positive. So I don't have any problems at the pieces themselves. But where I might have problems is where they hem together. And so I might have a problem at 1, or I might have a problem at 4. So I know that it's continuous on all of the real numbers, but I don't know about 1. So I guess it's continuous in all of the real numbers except for I don't know about 1 and I don't know about 4. So I want to check out the only possible problems are 1 and 4. So I want to ask myself, is it continuous at 1? So continuity checklist, right? So this is called f, so f at 1, and that's what they're wanting you to practice, this continuity checklist. So f at 1 it's defined, it's equal to 2. And then they want me to look at the limit as x goes to 1 of our function. And this is on a piecewise defined where you might have a problem. So you have to compare the left limit, which is as x goes to -1. So smaller, oh wait, 1 from a little bit smaller than, I got that notation going wrong there and said it wrong as well, a little bit smaller than 1, the left limit. So for the little bit smaller than 1, I would use this function, x squared plus 1. And since that's a polynomial, I can substitute in there, and when I plug in 1, you don't have to worry. The little negative up here said from the left side, which told me which function. And now all I have to, since it's a polynomial, all I have to do is substitute in. So this would be, I want it clear that I'm just substituting in 1. And so I'm going to get 2. Versus the right limit. So the limit as x goes to 1 from a little bit bigger than 1. And if I'm a little bit bigger than 1, I will use this function, 3 minus x. And because that's a polynomial, I can sub in. So this would be 3 minus 1, which is also 2. So what I know at part 3, right? So this is equal to 2, so I know it exists. And part 3 is the limit as x goes to 1 of f of x equal to f of 1. And we found this in part 2, which was coincidentally 2. And we found this in part 1, which was 2. So it's true. So it's continuous at x equals 1. I've spelled continuous wrong. I have one less u in it than I should have had. Whereas, so they asked me to find numbers where f is discontinuous, so I haven't found a number. So I'm going to ask myself the other question, is it continuous at 4? So when I go to look at 4, number 1, does f of 4, is it defined? And it is. It says equal to 4, use this one, so that'd be 3 take away 4 is -1. And then the next thing would be the limit as x goes to 4 of f of x. And so I would be looking at the left, and the limit from the left here. What function, if I'm a little bit smaller, it's 3 minus x. So I actually, this is okay to substitute, so I get -1. And from the right, I would have the limit as x goes to 4 from a little bit bigger than, and a little bit bigger than is the square root of x, which is the square root of 4, which is 2. But they're not equal to one another. So this is the problem, is that this does not exist. And so we know then it's discontinuous at x equals 4. It violates number 2 of the continuity checklist. So that's what they were asking us to do. So this right here, the only two problems places I could have a problem were at 1 and 4. So I told myself it didn't have a problem. I found out it didn't have a problem at 1. I didn't know before I started, but it did have a problem at 4. So this is the answer that they were hoping for there. And this is a justification of why I'm saying that that's the answer. And it's always important to justify your answer. At which of these numbers is f continuous from the right, from the left, or neither? So at 1, it's continuous from the right and the left. And so they only wanted to know about the discontinuity. So, and at 0, it's continuous from the left and the right. And at 67, it's continuous from the left or the right. 1 is no more special than any of those other numbers now that we verified it. But 4 is special. It was discontinuous, and they wanted to know, is it right-hand continuous or is it left-hand continuous? And if it's left-hand continuous, then we know that it would be true that the limit as x goes to 4 from a little bit smaller than will be equal to f at 4, right? If it's left-hand continuous. And you can kind of look and you can see what we had here and what we had here, that this is true. So we know that it's left-hand continuous. So that's what they were asking. It wouldn't be right-hand continuous because on the right, this is from the right, we got 2 where the function was equal to -1. So anyway, so it's easy to tell if it's left-hand or right-hand continuous, or if it was neither of those, which would have been a possibility as well. There could have been neither, but we saw that it was true, so we know that one. Okay, friends, 1.8, the last thing. A hole in the graph is called a removable discontinuity. So we had lots of discontinuities. We had holes. We had asymptotes. And we had jumps. And they said, hey, we're going to name one of those discontinuities. We're going to call it removable. And the reason that they're going to call it removable is that you could just simply redefine one point and then you would no longer have a discontinuity. Now that's not true of an asymptote, right? An asymptote, I can't, if I had an asymptote here and I'm going here and I'm going here, I can't remove the discontinuity just by putting in one point. But I can, if I have just a little hole in the graph, that means there's just a problem at one point. And so I can go fill in that hole. And it doesn't help on a jump either. So that's why they call it a removable discontinuity. So if you have something like this, that's a jump. And it doesn't help to fill in one point to make this continuous. You know, the Sesame Street definition of continuous is I can draw it without lifting up my my pen from the paper. And my comma got in my graph there a little bit. And so by filling in that hole, I can do that. I can just draw the whole thing without ever lifting my pen or my pencil. But I'd have to lift my pencil no matter if you put another dot on the graph or not. And the same here. I draw this and then I have to lift my pencil and then draw that. Okay, so here they're asking us, where is f discontinuous? So that's what they're asking about. And it's discontinuous on a rational function. You'll either have a hole or a vertical asymptote. Those are possibilities. You won't have a jump on just a rational function like this. So piecewise defined, you could have a jump as a possibility. Absolute value, you could have a jump because you could redefine it as piecewise defined, and then you could have a jump. So that's what I'm looking at. And where do those discontinuities come? They come when the denominator is equal to 0. And so I could factor this as a way of solving it. I could have also added 4 to both sides and taken the square root of both sides. So when I solve it, I get x equals -2 and x equals 2. So those are the discontinuities that I have for this function right here. And I haven't specified what kind they are, but that's what they're asking. Is they're in the next question, they're asking which, I think I must type that. What of these discontinuities is a removable discontinuity? I think the book probably asked which of these discontinuities is a removable discontinuity. And how you can tell if it's a removable discontinuity is it has to be a little hole in the graph. And it's a hole in the graph if when you factor the numerator and the denominator, so I'm going to do that. I already factored the denominator. Was x plus 2, x minus 2. I'm going to factor the numerator now, x to the third minus 2 to the third, that's what 8 is. and that's a difference of cubes. So this is a difference of cubes, and I have memorized the difference of cubes factoring formula. I have memorized it by singing a song, and if you like, I will sing that song for you, how I've memorized the formula. It's finger over threes, write what you see, which would be a minus b. Then it's square the first base. So the first base is here, the base. The base here is a. And the second base here, the last base, the base is b. So my song goes square the first base, multiply the bases together, and square the last base. And then the signs go soap. Opposite, same as I started with, opposite, always positive. So I sing the song when I have a difference of cubes. Finger over threes, write what you see, square, multiply, square, soap. That's my song, and that I can factor it from that little song. I know it's a silly song. I can also factor a sum of cubes, if something is a sum of cubes, from my song. The same song, finger over threes, write what you see, square, multiply, square, soap, and same as what I started with, opposite, and always positive. So this is the formula that I need, and my A is X and my B is 2, so I could plug all that in. Or I could re-sing the song just with this, and that's what I do. I don't write these out and then use the formula. You're free to use the formula. A lot of times calculus students tell me that they would prefer to use the formula than sing the song, and I'm okay with that. I personally like to sing. I'm not a very good singer, and so, but I don't mind singing. So right here, what would reduce out is x minus 2. And that was giving us x is 2. That was what was making, when x is 2, that's when our denominator is 0. And so that is the one that is a removable discontinuity. So which of these discontinuities is removable? X equals 2 is a removable. So at the place where x is equal to 2 is a removable discontinuity. And then they ask me, how would you redefine f of 2, because that's where it was removable, so that the graph would be continuous at that value. And how you would have to redefine that is just by finding the limit as x goes to 2 of your function, which I'm calling f, and I hope it is f. It is. And so this is the limit when I reduced it. Right? When I reduced it, it was this, x squared plus 2x plus 4 over x plus 2. So when I substitute in, I get 2 squared plus 2 times 2 plus 4 over 2 plus 2. So this is 4 plus 4 plus 4, that's 12, over 4, that's 3. So I would need to redefine f at 2 to equal 3, and then it would be continuous. Because remember that in order to be continuous, this has to equal that, right? And so since the limit is 3, we want f of 2 to also be 3. So we're using the continuity checklist for that, right? We know that if it's continuous, if the limit as x goes to 2 of f of x equals f at 2. And we found that the limit was 3, so that must mean that we want it to be continuous, so that means f of 2 must be equal to 3. So that's what they were asking for there. And then the other discontinuity was at x equals negative 2, and what type is it? And it is an asymptote, right? Because doesn't have the common factor, so it's an asymptote. So we did a lovely job at that, and I think that is the conclusion of 1.8. And so that's my story on that, my friends.